All right, next I'd like to talk about principles of humidity, and so we'll see how that relates to fog and also to cloud development. And so those are the processes that I want to go through in the next couple of lectures. And so first of all, we can think of humidity as being related to the amount of water that is in the air in a vapor state. And so, can water exist in the air in a vapor state? Absolutely. Water is a polar molecule, and so it can induce attractions to other air molecules, and it can remain suspended in the air without condensing out. This is possible. And under the right conditions, it's possible to get as much as 4% of your matter in the atmosphere in the water state. So it's possible then for the air to handle something like 4% of the total amount of molecules in the air can be water molecules. And it also turns out that the higher the temperature, the more water can be supported in the liquid state. So we're in the, in the vapor state here for water. So imagine that this is a water molecule. These are air molecules around it. These air molecules are going to move around and bounce off of the water molecule. And so that's going to knock the water molecule around, kind of randomly. And it's going to keep it from gathering together with other water molecules. And it's going to allow for the water molecule to be suspended. Now it's going to start to settle out, but if you crank up the speed of these molecules that are hitting it, then that can help to keep it from falling out under the influence of its own weight. Okay? And so we see that there is a temperature dependence on the maximum amount of water that can be supported in the vapor state. But you can get something like 4% of the mass of the air can be water under certain conditions. And so if you reach that point, though, where the air is saturated, then at that point, you're at what's called 100% relative humidity. Where we define relative humidity as equaling the actual vapor pressure divided by the saturation vapor pressure. And so typically then, the vapor pressure, of course we're talking about the water vapor pressure here, in relationship to the saturation water vapor pressure. And so this is the critical pressure here, the saturation vapor pressure, at which, when you reach that point, the air is completely saturated, it can no longer drop out, or can no longer hold water in the liquid state, and it starts to drop out as little water droplets. Okay, and so this is a function of temperature. And so if we plot the vapor pressure versus the temperature, we have a certain critical value of vapor pressure for temperature that is associated with the saturation. This is the saturation line. Where we're at 100% relative humidity. And so if we look up at the data projector for a second, we can see a figure that comes straight out of your textbook. And so these are specific values then for the temperature down here versus the vapor pressure up here. And the vapor pressure is typically measured in millibars. Where a millibar, if we have 1,000 of them, that's equal to, by definition, 1 atmosphere's pressure. So the total atmospheric pressure is about 1,000 millibars, but the vapor pressure of the water in the air is on the order of a few tens of millibars. So this might be millibar here. This might be, say, let's have this come into 0. And this might be 10, this might be 20, this might be 30. So it's a few tens of millibars is the portion of the total atmospheric pressure that is associated with the water vapor pressure. And so let's say here that we were at a temperature of 10 degrees centigrade, and we go across this way, we find that we get 100% saturation if the vapor pressure is 10 millibars. Okay, so this comes straight off the curve. So I could either, on a quiz or exam, give you the curve and have you tell you that the saturated water mixed in with the air is at 10 degrees centigrade, and then you could read off and you could see, well, that means that the saturated vapor pressure would have to be 10 millibars. Or I could just tell you what the saturation vapor pressure is at that temperature, and then you wouldn't need to look it up on the table. And so you could get that either way on a quiz or an exam. But let's just try this for a second with an example. Let's say that instead of us being at 10 millibars, let's say that at 10 degrees centigrade, the vapor pressure of the water is 5 millibars. So this is the actual vapor pressure, but either by being told that the saturation vapor pressure at 10 degrees centigrade is 10 millibars, Or by looking it up on the chart, by just going up to 10 and then across here and finding that this just, the 10s here are coincidental, that's the same number. That this corresponds to 10 millibars, you could get it from the table. And so then you could find the relative humidity. Or RH would be equal to 5 millibars, which is the actual vapor pressure, divided by the saturated vapor pressure, which is 10 millibars. And to turn that into a percentage, we would multiply by 100. And so that would give us 50% relative humidity. And so that's the way that you do a calculation at a particular temperature. But let's say that, so you're basically here at 5. So this is your vapor pressure, and let's say it's 10 degrees centigrade. But then, let's say that you maintain the same vapor pressure, but then later in the day, the temperature drops down to 4 degrees centigrade. And at that point, we reach 100% relative humidity. Because that's equal to 5 millibars. Here, this is your 5. It's intersecting the curve at 4 degrees centigrade, the way that I've drawn this here. So that means that because you're on the line, and this line is the saturation line of 100% relative humidity, it means that you're at 100%. Because now, the saturation vapor pressure is the same as your vapor pressure. So you're at 100% relative humidity. And so this can happen then. A lot of times there'll be kind of a moist day, and you'll be out camping, let's say. And then your sleeping bag's sitting out, and then it gets dark. You're sitting by the campfire, so you don't notice. But you've reached what we call the dew point. And that dew point is the point at which you've reached 100% relative humidity. And so at that point then, water droplets start to form because you can no longer, water can no longer exist purely in the vapor state if you try to add more water vapor to the system. Or if the temperature drops just a little farther than that, then that means you're going to have to stay on this line. That means that the rest of that water that's beyond 100% relative humidity is going to have to form droplets and drop right out on your sleeping bag. Your sleeping bag could be soaking wet. Or you could go outside in the evening. Oh, I forgot to get my paper this morning. It was delivered this morning, but I forgot to pick it up. And so you walk out on the grass where your paper was thrown out. It was nice dry grass in the day, but now it's all moist. And your socks are wet. I shouldn't have worn my socks. I should have put on slippers or my shoes or something, because now my socks are soaking wet. This is because you've reached 100% relative humidity. And at that point, the water starts to condense onto different objects like leaves or onto the ground and onto your newspaper, so your newspaper is wet too, or onto your sleeping bag. And so all of those things then are an indication of the change in the saturation point that is caused by the drop in the temperature. So as the temperature drops, these molecules are no longer moving as fast. Here's your water molecule, and here are the air molecules. That they're just kind of, they're going in every now and then they hit, but they're not moving as quickly because the temperature is lower. And so slowly but surely, these water molecules just drop right out of the air. And they can also, they're more likely to combine together into bigger droplets. And so you can get what are called condensation nuclei, in which you've got like a little piece of dust or something. And then as the temperature drops and these water molecules aren't being knocked around so much, they can start to collect on these little pieces of dust. Little pieces of dust typically are charged. The water molecule is charged. And so the positives and the negatives all attract. And so you start getting a water droplet that starts growing in size. So if you get water droplets that get bigger and bigger and bigger, then there's even more weight tending to pull them out of the air. And so at that point you start getting what we call condensation. Okay, and so that is the essentials then of how relative humidity relates to the saturation of the air. Now, if you were to go farther here, let's say you were to go to 2 degrees centigrade, then you'd be here on the plot, but because you're more than 100% relative humidity, that means that your pressure has to drop. Your vapor pressure has to drop to 100%, because the rest of that, what's more than 100%, is going to condense out as water. And so that means that you're essentially drying out your air by causing this condensation of the gaseous water molecules and turning them into a liquid. And the process of that happening, energy can be released. And so condensation is something that we'll see later can help to drive thunderstorms and are a source of energy for a lot of different weather phenomena. So using this idea, we can also talk a little bit about how this relates to fog. Now fog, put very simply, is just ground level clouds. So when you're walking through the fog, the misty fog on a kind of dank, dark day, you're walking right through clouds. You're in the middle of the clouds, and the clouds are on the ground. And so we might want to think about, well, why is this happening? Well, anytime that clouds form, they are forming basically from the condensation of water vapor on to tiny condensation nuclei. Now, these might be only be a 1/100th of an inch across, or less, these condensation nuclei. But the water molecules can start to collect on the small piece of dust, and so if that starts happening throughout the cloud, then we get the cloud is now in a state where it's kind of hard to see through it because of all the water that's connected in with these different little tiny condensation nuclei. And so here we could think of this as, for example, being like a dust particle. And so this all requires then that the system is at 100% relative humidity. And this tends to happen because of various reasons to occur on the ground rather than up in the air. So let's look at a few causes of fog. One, the acid fog. So here, the condensation nuclei, instead of being dust particles, might be pollution molecules. So you might have, for example, ozone, or you could have volcanic dust. Smog. And so an example of this then would be the London fog. London is kind of famous for its really foggy days, but it was worse around 1900. They were extremely foggy in those days, and they attributed that to the very bad air pollution. And so they cleaned up the air. The fog got better. It's not gone, but it got better. So that'd be an example of acid fog. Another type of fog has to do with what's called advection. Now that's the kind of fog we tend to get in California. Advection fog is associated with moist air traveling over cold water. And so that tends to happen then in Southern California. We have air that can move from north to south, or it can move from west to east into our area, but the water here is very cold. The reason the water is cold here is that we have clockwise circulations in the northern hemisphere of the ocean currents. And so what that has done along the west coast of the United States is to deliver freezing cold water from Alaska into our area. And although it's warmed up a little bit, it's still much colder than it is along the east coast. Whereas here along the east coast, what we have is still clockwise, but the last thing that it saw on the east coast is the equator. Okay, and so this is called the Gulf Stream. And that Gulf Stream gives rise to warmer water, which moves along the east coast of the United States. And so that warmer water gives rise to more humid conditions. Why is it more humid? Well, because you can have more water before you get to saturation as a vapor if the temperatures are higher. And the temperatures during the summer are higher, typically along the east coast, because that water, the last thing that it saw was the equator on its way up, and so that water is warmer. And so that means that the overall saturation vapor pressure is going to be higher, as we saw in the section on relative humidity, than it would be with cold water along the west coast of the United States. And so what will happen then is that the warm air is moving over the cold water. And so the heat then escapes, and this cools off the air mass. This lowers the saturation vapor pressure. As we saw in that last plot, here is our vapor pressure of the water. Here's the temperature, like this. And so we might be, say, over here, the air is at a higher temperature, but it moves over the water and the temperature drops until we reach saturation. So this is the temperature drop that is associated with moving over the cold water. And so that brings us to a cold enough temperature to where the motion of the air molecules is no longer sufficient to keep that water that's in the air in a vapor state. And so it starts to condense. So it condenses onto dust molecules, typically, to form ground level fog. So along the west coast then, we tend to get fog. Along the east coast, because the ocean temperatures are so high, this raises the saturation vapor pressure to the point to where we can have very high humidity. Okay? Because the temperatures are higher, that means that that water molecules can be held in the vapor state even if you have more water molecules in that state. And so you can start jamming in more and more water molecules until you reach a point where you have extremely high humidity. And so it gets to the point then on the east coast where you have to jump in the water because it's just too unbearable to be in such a high humidity situation. Why is that true? Well, because your method of cooling is to evaporate water off of your skin. But if there's already a whole lot of water in the air, then you're not going to be able to evaporate the water off your skin very well. And so that means that essentially you're going to do what you can to cool yourself off. You're going to start to sweat. But you're not going to be doing a very good job of cooling yourself off because it's the turning of the liquid to gas that lowers the temperature of your body, because your body then has to supply the energy to evaporate the liquid and turn it into a gas. And so that's why you feel so uncomfortable on the East Coast. On the West Coast, cold water and a lot of fog. Okay, and so that is that principle of the warmer air mass moving over colder water is seen here in Southern California, advection. But it's also seen on the other side of the Atlantic near England. See, in England, we've got the same kind of situation that we have here, where the convection is carrying the ocean currents from the Arctic. This would be Iceland up here, and then we'd be going down to England in there. And so you tend to get fog in England the same way that you tend to get fog in Southern California. So that's our second method, or type of fog, way that we can produce fog. The third way is with evaporation. Now in evaporative fog, essentially what we have is warmer water that wants to evaporate, but then you have a colder air mass moving over the warmer water. And so what does this do? Well, you get evaporation, and so these water molecules evaporate into the colder, drier air mass, but because the temperature has dropped, this cools the water molecules. And so they condense to form fog. Okay, and so there are other variations on this, but the basic idea is that somehow in a situation where you have fog, you have water molecules that are in the air that get cold enough so that they start to condense on particles of dust, and that generates your ground level clouds.